Hello, EEC 311 students. Because of the weather situation last week, I decided to try to record a couple of lectures online to make up for that missed time. So what I'm going to do in this lecture is I'm going to review problem 11.2 at the end of the chapter 11, and we'll talk about how to solve it with pencil and paper, and we'll also talk about how to solve it with PSpice. Okay, so you might notice that my voice is very scratchy. I've got some sort of a cold or sore throat or something, so bear with me, and I'm going to try to fight my way through this, this cold. Okay, so here is problem 11.2. We have a voltage source of 200 volts at an angle of 0 degrees, and it shows, and the problem statement shows a resistor of 30 ohms, an inductor with an impedance of J50, and a capacitor with an impedance of minus J10. Now, the first thing I want to do is try to determine the frequency and the value of the inductor and the value of the capacitor. So we don't need that information in order to solve a problem with pencil and paper, but we do need that information to solve the problem with PSpice. So we know that the impedance of an inductor is J omega L, and so we know that J omega L is J50. We know that the impedance of a capacitor is minus J over omega C. We know that that's equal to minus J10. So we get two equations. We simplify them slightly by getting rid of the J on both sides, and see that omega L is 50 and 1 over omega C is 10. We have two equations here and three unknowns, so there's an infinite number of solutions. Again, this is just for the PSpice simulation. So we can make some arbitrary choice here, choose some numbers that are convenient for us. So I'm going to choose omega equals 100 radians per second, L is half of a Henry, and C is 0.001 farads. Okay, so again, this is for the PSpice simulation. These values for omega L and C satisfy these equations over here. So now we have a circuit that we can use in PSpice. Now, the next thing that I want to do that we're going to have to know also for the PSpice simulation is to figure out what the frequency is in hertz. Well, we know that omega equals 2 pi f. That means f is omega divided by 2 pi. So this is an important equation to remember, and you'll have to have this memorized for your exams because it's very basic. So if I take omega equals 100 up here, divide by 2 pi, I get about 15.9 hertz. So I'm just going to keep this in mind and set it aside for now. And the other thing I need to know for the simulation is what the period of the voltage source input is. So remember, the period is equal to 1 over f. 1 divided by 15.9 is 0.062. So the period of that voltage input is 62 milliseconds. Okay, so again, just put this aside for now. Now the problem statement is right here. We want to find the average power supplied or absorbed by each element in the circuit. All right. So first, well, to solve this problem, I'm going to use Kirchhoff's voltage law to find the current I through the circuit. So we can see that 200 at an angle of 0 right here is equal to the current times this impedance times this impedance times this impedance. And that will give me Kirchhoff's voltage law, right? 200, let's write this 200, is equal to 30, that's this 30, plus J50 That's this J50 right here, minus J10 times the current. Got that? Good. So that means that current is 200 divided by this 30 plus J40. All right, so we can do that. Now, I know when you're doing your homework, you can use online calculators or handheld calculators. One tool that I found is the Kusashi.com, Cartesian, or you can do down here Cartesian polar. It's a little bigger for you. Or polar Cartesian or polar. You can do whatever you want to here. So I don't know, maybe there's some better online tools out there that you could use. If you have a better one, please let me know. I'd be glad to hear about it. So I'm going to do this 200, and the imaginary part of 200 is 0, divided by 30 plus J40. All right, so 30 plus J times 40. And now I can click on compute, and it tells me that the answer is 2.4 minus J 3.2, which I wrote here, 2.4 minus J 3.2. It also tells me the value of the value in polar coordinates. It's 4 at an angle of 53 degrees. Now this number is wrong, okay? I just realized this now. It should be minus 53 degrees. But, you know, you should be able to figure that out, actually. So in their algorithm here, they're not taking into account pluses and minuses correctly. But, you know, like, let's look at 2.4 minus J 3.2. So, like, let's see here. Find the whiteboard, okay. So, I can't draw straight with my mouse, but 2.4 would be like this much, and then minus J 3.2 would be down here, right? And so the total vector looks something like this. So it's a negative angle, right? So you should be able to see that, or maybe we need to find a better online tool or something like that. All right, so back to the computer. All right, so, but in general, this is a good tool. And then I can click over here on Cartesian polar, and so you can enter the first argument in Cartesian and the second argument in polar. The real and imaginary part of the Cartesian number, and then modulus just means the magnitude, and argument just means the angle in either degrees or radians, whatever you select. And then you can do subtraction or multiplication or whatever you want to do there. Okay. So back to the problem here. So we have 2.4 minus J 3.2, and that's the magnitude of 4 at an angle of minus 53 degrees. Okay, so now we have the current. Now what are we going to do next? Well, now that we have the current, we can figure out the power delivered by this voltage source. It's just V times I. But the average power is 1/2 times the real part of V times the conjugate of I. And this is the basic equation in the textbook in chapter 11. So 1/2 times the real part of V is 200 at an angle of 0. So that's just 200. I conjugate is 2.4 plus J 3.2. So if we carry out the multiplication and then just take the real part and divide by 1/2, we see that it's 240 watts. All right. So 240 watts is delivered by this voltage supply on average to the current. Okay, so now we need to find the average power absorbed by each of these three impedances, the and the C. Okay, so I'm going to go to the next page here, right here. All right, to find the average power absorbed by this resistor, we need to find the voltage across the resistor. That's easy. V equals IR. Well, we know the current on the previous page is this. The resistor is this. Multiply that. We don't even need a calculator to do that, I don't think. I'm going to get 72 minus J96 volts. And now the average power absorbed by the resistor is the same equation as we had on the previous slide page. 1/2 times the real part of VI conjugate. And now V is the voltage across the resistor. I is the current through the resistor. So it's 1/2. There's V, which we just calculated up here. And there's I conjugate, which we calculated on the previous page. And so you multiply that out, and you get this, and so it's 240 watts. Okay, so that's interesting because the power delivered by the voltage source was 240 watts average, and the power absorbed by the resistor is also 240 watts average. So what do you think the average power absorbed by the inductor and the capacitor are going to be? Well, they've got to be zero, or they've got to add up to zero, right, for conservation of power here. Well, we're going to go through it anyways, just for fun. So what's the voltage across the inductor? Here's the inductor right here. The voltage across the inductor, I times the impedance, right? There's the current, there's the impedance, J50, that's part of the problem statement, J50. Multiply it out, and you get the voltage across the inductor, 160 plus J120. So what's the average power absorbed by the inductor? Same equation as before. Now it's the voltage across the inductor and complex conjugate of current here. All right. Here's the voltage that we just figured out right here. Here's the conjugate of the current, which we figured out on the previous page. And multiply that together, lo and behold, this product here is equal to J800. J800 doesn't have a real part. The real part is 0. So we have in fact confirmed, and we have in fact confirmed that the average power absorbed by the inductor is 0. Go through a similar calculation for the capacitor, which I will not do. That is left as an exercise for the student to show that we also get 0 for the average power absorbed by the capacitor. So this is a general rule that whenever you see an inductor in a circuit, the average power absorbed by that inductor is going to be 0. The average power absorbed by any capacitor that you see in the circuit will be 0. Okay, so our powers add up. We have 240 watts delivered here. We have 240 watts absorbed here. 0 watts absorbed here. 0 watts absorbed here on average. These numbers are sinusoidal quantities, so these are just average. Okay, so now what do I want to do? Well, I feel pretty good about my results. Done here. Feel pretty good about my results because everything adds up. But I just want to make sure, just to make sure, I'm going to run PSpice. All right, so I installed PSpice. So it's in this Cadence folder. And the program you want to run is called OrCAD Capture CIS Lite right here. That's it. Okay, so let's run that program. Okay. Come up. It's coming here. Almost there. Good. Now, I want to create a new project. The name of the new project is going to be something meaningful like 11-2. and it's going to be analog, or mixed analog digital, but we're just doing an analog circuit here. Here's my location. Figure out the, location you want your PSpice files to be in and try to stay organized. Okay, so click OK here, and that's gonna. Okay, so yeah, I did this before, so you normally won't get this, but I'm going to replace the existing file, so I can start out fresh, and it's going to be a blank project. I'm going to create a blank project. Click OK. Comes up. Okay, there's. Okay, now I'm ready to put my schematic in here. All right, so let's do that. So place a part, and then this comes up. All right, now the first time you run, you may not have these libraries, so you have to click the little add library icon right here, and make sure you have all these parts selected, or all these libraries selected. Analog. So analog. So analog is added. Design cache. Is there design caches in here? Design cache. Maybe I don't have to add design cache. I don't know where it is. All right, so I think it's there already as a default. So eval is there. Add that. Source is there. Add that. And special is there. Add that. You can see there's like loads of libraries you can add here. All right, so now that's done. I want to first start. I want to create this this circuit right here. This is it. So I'm going to create this circuit in PSpice. Well, except I got to go to the previous one here. Yeah, here's the same circuit. Create the circuit, but I'm going to use these values for frequency, inductance, and capacitance. So let's stick on this page here. All right. Okay, so first I go to my source library, and I can add a sinusoidal input source, V sine. If I want a sinusoidal current source, I would add I sine. But we have a voltage source for this problem. So double click, and this appears. And then I just click where I want to put it. And then I hit escape on my keyboard, escape. And there it is. All right, now there's some parameters that are showing here. So can you see that? There's a little better. So V off, some sort of offset value. It's going to be 0. In other words, I think that's the mean of the voltage sinusoid. It's going to be 0. Amplitude. Amplitude is 200, right? 200 volts. 200 volts. Move that over. Oops. Frequency. We get for the frequency. Frequency is over here. 15.9 hertz. Keep doing that. All right, 15.9. Not being real exact, but 15.9 should be enough. There's an AC property. I don't even know what that is. So I just set it to 0. I don't even know what it is. All right, so there's my, somebody tell me what it is if you know, okay? Maybe I'll give you extra credit if you tell me what the AC property is. All right, so I got my voltage source. I need a resistor next, 30 ohm resistor. All right, so that's the analog library. And go down to resistor. Click there, place it right there. Hit escape, so I'm not placing it anymore. And it's going to be a 30 ohm resistor, so I double click on the number, change it to 30, and I've got my resistor. All right, what's next? My inductor's next. And the inductor is half of an ohm. All right, let's do an inductor. Here's L, double click, pops up, escape, half a Henry. Did I say half an ohm? Okay, then click on the value, set it 0.5. Default Henrys. Okay, 0.5 Henrys. And next I need a capacitor, right here, which has a value of 0.001 farads. All right, there's a capacitor. Capacitor is up here. Capacitor is the first one. Okay. All right, there's my capacitor. Escape. Right click. Rotate. Now double click on the value, and I want to set 0.001. Now everything's set. I got to wire it together. Click on the wire over here. Is this it? No, it's place wire right here. So click on that, and I go over here and go up and over there, go over there, there, and there, there, and there, and there. All right. So now that's done. And then the next thing I have to do is place a ground. I don't know why you have to place a ground, but in PSpice you have to place a ground. So right here, I have to click on place ground. There, this thing comes up. I don't have to do anything. Make sure the name is 0. Here it's 0 for me already, maybe because I used it before or something. I'm going to click OK, and I'm going to set it right there. Escape on my keyboard. All right, so move this up. Oh, that's weird. Okay, making things organized here a little bit. Okay, well, so what's next? Okay, now I need to create a go here to the PSpice menu and create a simulation profile. So click on new simulation profile. I'm going to call it 11-2. I'm going to click on create, because problem 11.2, click on create. Now, this is kind of funky, but this simulation settings comes up, but it doesn't come up in the window, so I have to click on it down here. And this is just all some default stuff. And you can, change it to whatever you want to for now. I'm going to leave it to the default. Click OK. Okay, now, what else do I want to do? Well, it seems to be a little bit easier to plot things if you're PSpice here, click on markers. I want to add markers, so I'm going to record the voltage right here. I have to collect voltage being more or less connected to a wire bus or pin, so I tried to connect the wrong end of it or something, so I'll put it like right there. Escape. So I already know what the voltage is there, right? It's 200 volts with 0 at this frequency with 0. That's what AC is. I think you can, let's see if I right click on this, edit properties, AC. Maybe AC is the phase offset. I think that's it. I don't know if there's a phase variable right there. So that's not it. Okay, so go back to page 1 here. Okay, so I'm going to plot the voltage there, even though I already know what it is, just for comparison purposes. I also want to plot the current at this point. So I'm going to go to PSpice, markers, current into pin. And if I try to put it on the wire, I can't. I have to connect it to the pin of one of these devices. So like, the pin of the voltage source, and the pin of something. I can connect it anywhere because the voltage is the same all the way around. So I'm just going to put it right here. Escape. And I hit the run PSpice I should save it, save document right there. Make sure I don't lose an hour's worth of work. And something crashes, and run KeySpice right up here. And everything works correctly here. No error messages. You see this thing flashing down here? So I click on it, and it shows me my markers, or my values of my current and voltage. Okay, so this is like kind of weird, right? I mean, it doesn't look like a sine wave. So what happened? Anybody know? I can see you all raising your hands, but this is not interactive, so I can't call on you. Right, the simulation length is only 1 microsecond. You can see the 1 microsecond here. And the period of the input source is 62 milliseconds. So it's like we're only plotting the first tiny fraction of the sinusoids in this circuit. So you want to set the period, you want to set the simulation duration to, a few periods at least, right? Maybe 5 periods. That would make 300 milliseconds. So what I need to do is I need to go back here, I need to go back up to PSpice, edit simulation profile. Instead of 1,000 nanoseconds, which is a microsecond, that's crazy. No, I want to do 300 milliseconds right there. And there it is. So PSpice is not very smart regarding figuring out a default runtime. It's the t-stop value. But we have to tell it, make sure we get the right simulation length. Click OK. Now, I have to go back up here, click on Run again. Okay, so that looks a little bit better, right? I have my voltage source, which is 200 volts at an angle of 0. And I have my current down here, which is much smaller value of amperage. All right, so something I want to point out here is that you notice that the voltage source is a sinusoid. Right? This is a sine wave at an angle of 0 degrees. But in the text, when we talk about a phasor, if in the text we said 200 at an angle of 0 degrees, that would be a cosine wave. Like this, and so forth, right? So in the text, 200 at an angle 0 degrees means a cosine wave with a phase offset of 0. In PSpice, 200 at an angle of 0 degrees means a sinusoid. So I think I mentioned once during class, it doesn't matter which way we define our phasor. It's 200 at an angle of 0 degrees, a sine wave or a cosine wave. It doesn't matter as long as we're consistent. So the book's consistent one way, PSpice is consistent the other way. Well, you just need to be aware of that difference. There's one other thing I want to point out here, and that is that sinusoid looks like a little bit choppy. It's like, straight line, straight line, straight line. The sinusoid doesn't really look that smooth. And the reason is because it's using an integration step size or a simulation step size that is too large. Right, so if I look at the time length here, this is a 300 millisecond simulation. I want to really have at least 100 time points in here to get smooth results, maybe even 1,000 time points in here. So if I have a simulation time of 300 milliseconds, my minimum step size for simulation should be, say, 300 microseconds. So again, I'm going to go back here to my schematic, click on PSpice, edit the simulation profile again. And when I see maximum step size, I'm going to enter 300 microseconds. Shorthand notation US in PSpice. So it'll give me a 1,000 simulation steps for the entire simulation, which would give me a smoother output. Still, I have to run the simulation over again, go up here, run it, and okay, coming up. Okay, I like that a lot better. Looks a lot smoother. It actually reaches 200, you know, and minus 200 every cycle. So, yeah, nice and smooth. Okay, that's good. That's good. All right, so now, what do we want to do next? A couple things I'm going to notice to confirm my paper and pencil results. Check something here. Okay, yeah. I'm going to notice that the input voltage crosses 0 at 62.9 milliseconds. Okay, so how can I see that? Well, I go up here. Here's the input voltage. This, you can see the key down here. The input voltage is this green trace. I can go up to click on trace, click on cursor, display, and then I just click on the window here. And now this comes up down here in the bottom right corner. It shows me where the cursor is in the plot window. It's at 43 milliseconds, right? It's at 43 milliseconds. The voltage trace is minus 187 volts. That's right here. And the current value is 2.2 amps. That's right here. So to find the time at which the voltage crosses 0, that will be 1 period. I can just click on the vertical bar here, drag it over until I get close to 0. Like right about there, there's about where the green line, the green trace crosses 0. And I can see the green trace is like minus 0.99. And I can come up here and click on it again. I can use my arrows on my keypad. Can you see this number changing? As I click the arrows on my computer keyboard. So I'm trying to find out where it crosses 0. So it's somewhere like right between here and here, right? There, it's minus 39 milliseconds. I mean, minus 439 millivolts. Here it's plus 439 millivolts. So it's like halfway between 62.871 and 62.915. So let's call it 62.9 to round it. Now I want to find out, so that's where the input voltage crosses 0. I'm going to find out where the current crosses 0. Well, here's the current, is this red line, red trace, and it crosses 0 a little bit later here, right? So I'm going to drag the cursor over here, and it's right here. So the current at this point, 68 milliseconds, the current is 2.2 amps. And I'm going to use the arrow keys on my keyboard. Oops, I got to click up here first. I got to drag it over to the right spot. All right, now I can use my arrow keys, I think. Yeah. And the current, and I'm trying to get the current. Yeah, there's the current. Where does the current cross 0? So I'm just going back and forth with my arrow keys to get this number, current, as close to 0 as possible. Minus 13 milliamps, 20 milliamps, minus 64 milliamps. So it crossed 0 right around 73.6 milliamps. Right in there. So back here, let's call it 73.566 milliseconds. Milliseconds is where it crosses 0. Okay, so that means the current phase is the difference in time the difference in the current phase, because the input voltage phase is 0, so that means the current phase is the difference in time between these, where these two cross 0, scaled to 360 degrees. Right? So it's this 73 minus 62 milliseconds. 1 period is 62.9 milliseconds. So this quotient right here is the fraction of 1 period that the current is offset from the voltage in terms of phase. So I multiply that by 360. And so when I do that math, I get 61 degrees lagging. Now I know it's lagging because I go back over here and I see that the current is crossing 0 after the voltage crosses 0. So this is actually, it's negative also. Okay, so, but in any case, I'm going to stick with my notes here, and I've got 61 degrees lagging, which means that the phase of the current is minus 61 degrees. All right, so if I go back to what I calculated as the current, I calculated that the current was right up here. Where did I calculate the current? It was over here. I calculated the current phase was minus 53 degrees. So that doesn't quite match my minus 61 degrees. I'm off by about 8 degrees. I mean, you might think it's close enough, but why is it 8 degrees off? Well, the reason it's 8 degrees off is because remember that phasor mathematics in circuits applies only to steady state quantities. So the input voltage is always at steady state because it's an input voltage. The current is not always at steady state. The current takes time to reach steady state. And it looks like a steady state sinusoidal current here, but it's not actually steady state. There's some initial conditions that you know about transients from circuits 1, and there's some initial conditions that haven't yet died out. So we can get a more accurate answer for our phase if we look over here. So what I'm going to do is, because over here is where those transients have died out. So what I did was I looked where the voltage and current cross 0 toward the end of my simulation profile. And again, it's around 250. So I do the same thing that I did before. Find out where the voltage crosses 0 using my arrows on my keyboard to move the cursor slightly until it gets to 0. Again, it's right between this value and this value. So it's right around 251.5 something milliseconds. So I wrote down 251.639 milliseconds. Then we do the same thing for current. Where does the current cross 0? Current cross 0 like right over here. So I'm going to need to move the cursor until this current gets down to 0. Okay, so it's getting closer to 0, 837 milliamps. 64 milliamps minus 84 milliamps. So this is pretty close, 260.9 milliseconds. So here's the value I wrote, 260.861 milliseconds. So what's the phase of the current? The phase lag of the current is 260 minus 251 milliseconds, scaled to the period of the input source, the voltage input, and then times 360 degrees to get the value in degrees, and I get 52.8 degrees, and that's basically exactly what I calculated over over, it's the first one right here, calculated minus 53 degrees, and I get 52.8 degrees phase lag, so the phase would be minus 52.8 degrees. So that's it. We can also confirm the magnitude. So the magnitude is 4 amps. So yeah, 4 amps. So again, I can go to my plot and like, kind of get to the peak. See, there's the peak of the red wave form, which is current, and I can use my cursor, my arrow keys to move it until I find the peak here. It gets up to it's more than 4 point, that was it, 4.0062. So that's pretty close to 4 amps. So that part's good. Now what about average power? So that's one more thing I can do here. The average power delivered by the voltage source can be evaluated with this function in PSpice. I have no idea why it's so weird looking, but there it is. Y at last X average WV1. Well, the WV1 part makes sense. So W, like if you go up here, you can click on trace, add trace, and this shows all of the quantities in that circuit that you can evaluate. Voltages and currents and power. Power is indicated with W for watts. So you notice that there are things like you have a voltage at either end of resistor R1, the voltage at the first node of R1, or the voltage at the second node of R1. So those, depending on which direction you put your resistor in, you have to figure out which voltage you really want to include in your plot or in your equation. Well, delete those and go down here. I can look at W V1. That is the power delivered by voltage source V1. Right, the voltage source is V1. It's called V1 right here. All right, so what did I say? Is it like Y? It's one of these equations. It should be. It's not over here. But there's average right there. It doesn't really put it in the right order unless you have to do that more manually. So WV1, and then I have to add Y at, what was it? Right here. Y at last X, average WV1. Y at last X, average WV1. Make sure my parentheses are balanced, and click OK. And it's invalid. So Y at last X, average. What did I do wrong? Y at last X, AVG WV1. Oh, it's not a trace expression. I'm going to copy it, cancel out of here, and instead I want to go to trace, evaluate measurement. That's what I need to do. I can't plot the average measurement. I can just evaluate it. So now I'm in the evaluate measurement window here. I can put my Y at last X, average WV1, click OK there, and it tells me minus 246 watts, which closely matches the 240 watts that I calculated here. It's negative because the voltage source is delivering power to the circuit. So the voltage source is, losing power on average. And it's not exactly minus 240. It should be minus 240 exactly, but there are always some approximations when you run a simulation like this. So if you get the answer with paper and pencil, you should always get a more accurate answer as long as you carry enough significant digits through in your calculations. You should always be slightly more accurate than the simulation. Okay, so I can close this window, and I can go back to PSpice here, and I can close all of this. Save that. Close. These are some extra files that PSpice uses. Okay, so that's an example of how to use PSpice and to evaluate power quantities and to confirm your paper and pencil results with PSpice. So I hope that's been helpful. Send me an email if you have any questions or comments. And thank you. Goodbye.